Okay, so here is a video on side analysis of curves. So we have a word problem, and then we are given a function p of t, which signifies the size of the virus population growing at each hour. And then we're asked to find at what interval is the rate of the population growing increasing. So it's asking when the rate is increasing. So it's asking when the rate is increasing. So it's not just p of t that we're considering right now. Okay, so first we need to find the derivative of p of t. So we can say 2t negative and then sine t squared minus cosine t, right, times e to the cosine t squared. So when we take the derivative of p of t, we get this value right here. Okay, and then since we're trying to find a rate when the rate is increasing, we do have to see p double prime t. So we have to find when p double prime t is positive to find when the p prime t is increasing. Okay, so we have a product rule question here, right? So first, -2 sine t squared, right? -2 sine t squared, and then plus 2t cosine t squared times -2t, and then plus sine t e to the cosine t squared minus sine t plus 5, and then plus -2t sine t squared minus cosine t to the power of 2 e to the cosine t squared minus sine t plus 5. So obviously, as you can tell, this is pretty complex. So then that's what we're going to do. We're going to put everything into a graphing calculator. We're going to graph this and see when the function is increasing. Okay? Okay, so for me, I found values or the intervals where p double prime t is positive. So p double prime t is positive on 0 to, I'll just do non-inclusive, so 0 to 0.669, and then from 0.699, oops, 9 to 2.358 would be the intervals. So the virus population growth rate is increasing on this interval. Okay, and then at what value t is the size of the virus population at its maximum? Alright, so the size of the virus population at its maximum can be given by considering some candidates. So first we need to consider some critical points, I guess. So this is when p prime t is equal to 0. So let's find out. Okay, so for me, I found the 0. I only found 0 on the interval. So the 0 was 1.757. So here is one candidate, and then we also have our intervals 0 and 2.5, right? So we have t, 0, 1.757, and then 2.5, right? So the only thing we need to do right now is to plug in these values to p of t. So let's plug it in. Alright, through my calculations, I found that p of t is at its maximum when t is equal to 0, which might seem a little bit odd since the population is supposed to be growing very rapidly. But then on this interval specifically, I think the starting point has the greatest number, and then in other intervals as we progress through, it's going to fluctuate a lot from increasing, decreasing, increasing to decreasing. But right now it's decreasing. Yeah. So that can probably be attributed to some deaths in the virus population. Okay. At t equals 0, the size of the virus population is at its maximum based on the candidates test. The maximum value so here's our answer. And then going off to number 2, given a function f of x equals sine x to the third times sine x, find the following values on which intervals is the function both increasing and concave down. So for this, we need to find when f prime x is greater than 0 and concave down, f double prime of x is less than 0. F prime of x is going to be 3x squared sine x plus 3x to the third cosine x, right? Okay, and then f double prime of x is going to be 6x sine x, and then plus 3x squared cosine x plus 3x squared cosine x minus x to the third sine x. Okay, the function is both increasing this interval values are positive and negative respectively. Okay, so the question asks, does the function have any points of inflections? So points of inflections are when f changes signs, right? And then going back to the graph that we drew, this is also on the interval 2 to 5. So going back to the graph that we drew, looking at the f double prime function, we actually have 1 point of inflection at x equals 4.267, so, or about equals, so this will be our point of inflection. Okay, so I'm gonna write f double prime of x has f prime of x f of x has a point of inflection at 4.267. Oh, and then we should plug this back into our equation. So 1 second. 4.267 is going to be plugged in. Okay, and then we get an answer of 996. Because f double prime of x changes signs from negative to positive here. Okay, last part of the number 1 problem. So if a midpoint Riemann sum is used to approximate the area under the curve from x equals 2 to x equals 4, would the approximation be an underestimate or an overestimate, and why? So what we have right here is a midpoint Riemann sum, and for midpoint Riemann sums, if the graph at a certain interval is concave down, then the midpoint Riemann sum is going to be an overestimate. If it's concave up, it's going to be an underestimate. So since we actually have an concave down function for f of x from x equals to 2 to x equals to 4, right? Because on the previous problem, we saw that there's only one point of inflection from the interval 2 to 5, and that was at 4.267. So from 2 to 4, there is no other point of inflections, or meaning like there is no change in the concavity. And then the concavity here is concave down, so it's going to remain concave down. So since we know that on this interval the function is going to be concave down, the midpoint Riemann sum is going to be an overestimate. Okay, so midpoint Riemann sum approximation of f of x from x equals to 2 to x equals to 4 is an overestimate because on this interval function is concave down, and taking the midpoint Riemann sum approximation of a concave down function, it would be an overestimate. Right, so this is going to be our justification.